stronger than steel, lighter than aluminum, cheaper than almost everything we use today. Yet most of the world hasn't even heard its name. Imagine a skyscraper that bends instead of breaks in an earthquake. A jet that burns a fraction of today's fuel because its structure weighs next to nothing. A phone case so thin it feels impossible, yet you couldn't dent it with a hammer. That future material isn't sci-fi alloy or alien metal. It's carbon reorganized. One atom thick, perfectly patterned, and it might end steel's 150-year reign as the backbone of civilization. Its discovery began, unbelievably, with Scotch tape. Scientists peeled away layers of graphite until a single sheet remained. A sheet now proven to be about 200 times stronger than steel and almost weightless. They called it graphene, but graphene is only the start of the story. Behind it, an entire class of next-generation composites is emerging. Carbon nanotubes that can lift satellites, glass nanolattices lighter than air yet harder than titanium, even protein-based polymers inspired by spider silk. Together, these breakthroughs are rewriting the laws of materials science and forcing industries to ask a terrifying question. What happens when the world's most essential material becomes obsolete? Because when steel looks heavy, expensive, and old, everything built from it does too. And in the next segment, we'll uncover how a single layer of carbon may be about to collapse the foundations of modern manufacturing and launch a trillion-dollar race to replace steel itself. For a century and a half, steel has been humanity's unspoken superpower. It frames our cities, drives our cars, and anchors our global economy. The Eiffel Tower? Steel. The Golden Gate Bridge? Steel. Even the phone in your hand likely started its life on a steel assembly line. It's the skeleton of civilization, sturdy, familiar, dependable. But progress doesn't care about tradition. Underneath that stability lies a quiet truth. Steel is heavy, inefficient, and energy-hungry to produce. It takes almost 2 tons of CO2 to make 1 ton of steel. Multiply that by nearly 2 billion tons produced each year, and you get roughly 7% of global emissions before construction even begins. Now picture materials 200 times stronger and 100 times lighter, built from carbon sheets so thin light can pass through them. They promise aircraft that use 10% less fuel, electric cars that gain 50 miles of range overnight, and buildings that consume no reinforcing concrete at all. For the aerospace industry, every kilogram saved means less fuel and lower costs. For construction, lighter materials mean smaller foundations and freer forms. The numbers aren't subtle, they're seismic. Yet the same promise that thrills scientists terrifies industries built on the old order. A $3 trillion steel economy doesn't fade away quietly. Factories, supply chains, and entire national exports depend on this metal. The emergence of something better threatens not just material science, but geopolitical balance. So the stakes aren't just scientific, they're economic, environmental, and existential. Because if a lab in Cambridge or Seoul perfects the recipe for industrial-scale graphene, the world's supply chains and power structures won't look the same within a decade. And in the next segment, we'll step into the labs themselves to see how researchers are bending physics with carbon nanostructures that could literally support an elephant on a pencil tip. To understand how one material could dethrone steel, you have to start impossibly small. Graphene is a single layer of carbon atoms arranged in a honeycomb lattice so perfect it looks computer-generated. 1 atom thick, 10 million sheets of it stacked would barely equal the width of a human hair. Yet it holds an almost absurd strength, about 130 gigapascals of tensile power. That means a thin graphene film could, in theory, support the weight of an elephant balanced on a pencil point without tearing. But graphene is more than strong. It's alive with conductivity. Electricity moves through it faster than in copper. Heat races across it quicker than in diamond. It's flexible, transparent, and nearly massless. Those features fuse mechanical, thermal, and electrical superiority in a single sheet, something no previous material has done simultaneously. Carbon nanotubes take it a step further. Imagine rolling that single-atom sheet into a perfect cylinder and locking it tight. You've created a structure with strength up to 150 gigapascals and density, so low it can float on air currents. Add millions together, and you get composites that outperform metals while weighing a fraction as much. Then there are glass nanolattices, architectural materials strengthened by geometry instead of chemistry. MIT scientists built lattices 5 times lighter, but 4 times stronger than steel. Proof that the shape of matter can now matter more than the matter itself. All rely on the same revelation. Design at the atomic and nanoscale gives humans mastery once reserved for nature. We're no longer limited by what elements are, only by how we arrange them. And that realization doesn't just challenge steel's dominance. It flips our entire manufacturing philosophy. Because what happens when the way we think about materials changes more radically than the materials themselves? That's exactly what Segment 4 will reveal. How the rise of engineered atoms could upend industries, rewrite economies, and blur the boundary between matter and imagination. For centuries, we've improved materials by mixing, forging, and refining, engineering on the macro scale. But graphene, nanotubes, and nanolattices mark a moment when we stop combining elements and start designing matter itself. Think about that. Engineers aren't just shaping steel beams anymore. They're engineering the atoms inside the beam. The strength once achieved by brute force and heat is now achieved by pattern, geometry, and quantum precision. Welcome to the era of engineered atoms, where physics becomes a design tool. Here's the twist. This revolution doesn't just threaten the steel industry. It threatens the entire logic of manufacturing. Why melt ore in furnaces when you can print a structure atom by atom with zero waste? Why ship raw metal across oceans when materials can be synthesized locally in labs the size of garages? Once materials can be designed like software, supply chains collapse, and the world retools itself around digital fabrication instead of blast furnaces. The implications are staggering. A 70% reduction in industrial emissions. Aircraft that weigh half as much but last twice as long. Bridges and buildings that heal microscopic cracks before they fail. But perhaps the most startling shift is philosophical. Steel was humanity's symbol of permanence, of industrial might. Yet the strongest material ever created is also the most fragile to hold. A film invisible to the naked eye. Power, it turns out, no longer looks like mass. It looks like mastery. And the question now isn't can we replace steel? It's what kind of world is built when matter itself becomes programmable? Because in that world, even the laws of failure start to disappear. And that's where the final segment takes us, into a future where impossible materials redefine civilization itself. Picture a skyline that glows at night. Not from light bulbs, but from the materials themselves conducting light through carbon veins thinner than dust. Picture ships that cross oceans using half the fuel, and rockets built from structures lighter than air, yet strong enough to breach orbit. That's not a dream. It's the trajectory we're already on. Steel built the industrial age. Engineered carbon will build whatever comes next. Once graphene and its cousins scale beyond the lab, the shift will feel instantaneous. Supply chains will shrink. Architecture will float. Energy consumption will plunge. Even space travel will change. From brute force rockets to elegant elevators made of materials that seem to disobey gravity itself. But the deeper transformation isn't physical. It's intellectual. For the first time, we're teaching matter to obey design instead of discovery. We've entered an era where chemistry, physics, and imagination are merging into one language of creation. It's worth remembering, when aluminum was first extracted in the 1800s, it was more precious than gold. Within decades, it was the metal of flight. The same arc is already unfolding for graphene, nanotubes, and nanolattices. Their price will crash, their production will scale, and their impact will outlast every revolution before them. Because the future isn't forged in furnaces anymore. It's woven, printed, and grown, atom by atom. And when the strongest material on Earth weighs nearly nothing, the idea of what's impossible becomes weightless too. This is the new forge, the place where the next age of civilization begins.